Hello everyone, welcome back to this online class. Today we are going to look at ODEs of the first order and first degree, and in particular we are going to look at how to solve linear ODEs. Now we are given this problem that solve the following differential equations. In part A we have dy over dx plus 2x times y is equals to 2x, subject to the condition that when x is equals to 0, y is equals to 4. In part B, we have 2y plus x raised to 6 times sine x dx minus x dy is equals to 0. And in part C, we have x plus 2y cubed dy is equals to y dx. So all these equations are linear ODEs of the first order and first degree. We need to see how to solve each of them. Now, even before we look at the solution of those equations, let me give you a general form of a linear ODE. So you can just write a note, NB, that a linear ODE has the general form dy dx plus a function of x, let's call it p of x times y, is equals to another function q of x. This is a linear ODE in the dependent variable y. So this equation is linear in y as the dependent variable. So to solve this equation, we are going to use what is called the integrating factor method. So this is what we call integrating factor. Integrating factor. We denote that by I dot F to mean integrating factor. So to get the integrating factor for this equation, it is given by integrating factor is equals to exponential the integral of p of x dx. That's the formula for getting the integrating factor. I'll tell you how to apply that integrating factor method to solve the linear ODE. So you realize that the one that I've written here is linear in the dependent variable y and independent variable x. You may also have dependent variable to any other variable different from y. Let's say where you have the dependent variable to be x instead of y. So another form of a linear ODE, let me write number 2. You could also have dx over dy plus a function p of y times x is equals to another function q of y. Now this is linear, but in the dependent variable x. This is linear in x. So how do we find the integrating factor for this one? Integrating factor is equals to exponential the integral of p of y dy. So we have just changed the roles of x and y. If you compare equation, the first one and the second one, you realize that where there was y, now we are using x, etc. Or you could have any other variable. It doesn't have to be x and y only. You could use pq, or you could use any other variable, m, n, etc. So having explained the general form of a linear ODE of first order, let's now see how to solve the first part. That's A, dy over dx plus 2xy is equals to 2x. So the first one, you write A, dy over dx plus 2xy is equals to 2x. And the condition is that y, when x is 0, should be equal to 4. So let's first of all find the general solution, and then we apply the given condition to find the particular solution. So when you compare this with the first form, dy over dx plus p of x times y is equals to q of x, you realize that our p of x is positive 2xy. This is our p of x. The other one is q, but when finding the integrating factor, we are all interested in knowing the p of x in this case. So let's integrate it. So the integral of p of x with respect to x is simply equal to the integral of 2x dx. And this is equals to x squared. Some of you will write a constant of integration. Don't write a constant of integration. So you need to take note that when you're finding the integrating factor, don't write the constant c of integration. Why? Because this constant, we are going to write it in the final solution, the general solution. It will be taken care of in the general solution. So therefore, our integrating factor is simply equal to exponential the integral of p of x dx, and that is the same as exponential x squared, because we got it here. So now multiply the ODE by the integrating factor. So you multiply the ODE by the integrating factor on both sides. So what are you going to get? It will be exponential x squared dy dx plus 2x exponential x squared y is equals to 2x exponential x squared. So that's what we have. Now look at the left-hand side of this equation. This left-hand side can be grouped as the derivative with respect to the independent variable. In this case, the independent variable is x, of the product of the dependent variable, which is y, times the integrating factor, which we got as exponential x squared. Because if you use product rule, you'll go back to the left-hand side that we had up there. The right-hand side, we don't interfere with it. That is 2x exponential x squared. That's what we have. Now, I need to integrate this. Remember that once you have multiplied a linear ODE by the integrating factor, you need to take note that the left-hand side will always be equal to the derivative with respect to the independent variable of the product of the dependent variable and the integrating factor, just like we have done here. So if you cross multiply, if I cross multiply by dx, I'm going to get dy times exponential x squared is equals to 2x exponential x squared dx. That's what we have. And now you need to integrate both sides. Integrate. And I told you that integral and derivative are inverses of each other. So on the left-hand side, those two will cancel out so that we only remain with y times exponential x squared. So we'll say here, or y times exponential x squared should be equal to, the question is, how do you integrate this? Somebody will use integration by parts, but will it work? The easiest is using the u substitution. So you let let u be equal to x squared. So that is our u. Now we need to find the u, the x. So from here, the u, the x is equals to 2x. So this simply means that, let me write multiply. That means the u is equals to 2x dx. So where we have 2x times dx, that is the u. And where we have x squared, that is u. So this integral can as well be written as now the integral of exponential u du, which will give you exponential u plus a constant c. And what is exponential u? U is the same as x squared, so exponential x squared plus c. So this is the same as exponential x squared, then there's a constant c of integration. You see, now we are adding the constant at the solution step. We don't write it when you're finding the integrating factor. You write it at the final solution. And so from here, you can make y the subject. So you divide through by exponential x squared. So you can write or y is equals to 1 plus c over exponential x squared. And when you want to check this up, let me use another color. This can also be, when you use the lots of indices, this can also be written as, you can write or y is equals to 1 times, not times, but plus exponential, c times exponential negative x squared. That is our general solution. General solution. Why general solution? Because it involves the essential arbitrary constant. It is the primitive corresponding to the given differential equation. That's how we define a general solution. We need to find a particular solution for this equation. So we have to apply the given condition. That's an initial condition that when x is 0, y is equals to 4. See, the condition I'm talking about is this one. So when we apply this, we are going to get the particular solution. So this means that when x is equals to 0, comma, y should be equal to 4. So let's substitute that into our general solution so that I need to put x is equals to 0 and y is equals to 4. So what do we get? That will give us 4 is equals to 1 plus c exponential 0. Anything raised to 0 is 1. So this simply means that 4 is equals to 1 plus c. And so therefore, you get c to be equal to 3. So that's the value of the arbitrary constant. And so when we replace it back to our general solution, we get our particular solution as, so you can just say hence, our particular solution would be y is equals to 1 plus 3 exponential negative x squared. So what I've written here is the particular solution. Particular solution. And you need to take note, there's a difference between general and particular. In general, we have said that it is the primitive corresponding to the given differential equation. In particular solution, we have said it is obtained from the general solution by assigning numerical values to the essential arbitrary constants. And how do you get those values of those constants? You apply the given initial conditions. Take note of the difference between the two. In part B, let me write it here. In part B, we are solving 2y plus x raised to 6 sine x dx minus x dy is equals to 0. So clearly this equation cannot be linear in x. Why? Because of x raised to 6. When we talk of linear in a given variable, the power of that variable must be 1, not any other power. So it cannot be linear in x because of x raised to 6. What about the powers of the variable y? You see the power here is only 1. I can't see any other power of y. So this equation is linear in y. So you are going to write that in the form of dy over dx plus p of x times y is equals to q of x. So let's rewrite this equation in that form. So I'll start by taking this to the right hand side so that we have 2y plus x raised to 6 sine x, this is dx, is equals to x dy. Then I need to divide by dx, so both sides. Of course, I need to divide here by dx and also here by dx. So the dx will cancel, this dx will cancel. So this means that x times dy over dx is equals to 2y plus x raised to 6 sine x. But you see, the coefficient of the derivative must be 1. So get rid of this x. So divide both sides by x. So here we are going to divide by x. Again here by x. You must make the coefficient of the highest derivative in that equation to be 1. So by doing that, this is what you're going to get. So this implies that now dy over dx, this should be y, dy over dx is equals to 2 over x times y plus x raised to 5 sine x. And then you can now rearrange. You can say or dy over dx minus 2 over x times y is equals to x raised to 5 sine x. So that's now linear in the dependent variable y. So you can write here, this is linear ODE in the dependent variable y, and the independent variable here is x. So this one here, the whole of this coefficient of y, that's negative 2 over x, is what you are calling p of x. So this is p of x. This other one is q of x. Now, we need to integrate p of x with respect to x. So I need the integral of p of x dx. What is it equal to? That's the integral of negative 2 over x dx, which is the same as negative 2 ln x. And how else can you write this? This is the same as ln of x raised to negative 2. When you apply the laws of indices, the laws of logarithms, I mean, because this one will be the power of the parameter x. Remember, m log a is the same as log of a raised to m. That's what I've used. Now, the integrating factor is exponential, the integral of p of x dx. And so this will be exponential. What did we get? It was ln of x raised to negative 2. And you see, exponential function and natural logarithmic functions, they are inverse functions of each other. So this and this will cancel out, so that our integrating factor will be x raised to negative 2, which is the same as writing 1 over x squared. Now, the next step, you multiply the linear ODE. Let's call it this one, the equation star. You can call this equation star. So that's what you multiply by the integrating factor. So you can write multiply equation star by the integrating factor, of course, on both sides. So we'll have 1 over x squared times dy dx minus 2 over x cubed times y is equals to, remember, x raised to 5 divided by x squared, that is x cubed. That will be x cubed times sine x. So once you multiply that linear ODE by that integrating factor, you need to take note how the left-hand side can be rewritten. So I said this is the same as the derivative with respect to the independent variable, in this case it is x, of the product of dependent variable. Our dependent variable here is y, and the integrating factor, which is 1 over x squared. So it must be product of dependent variable and the integrating factor is equals to the right-hand side, which is x cubed sine x. If you cross multiply by dx, this is what you're going to get, or dy over x squared is equals to x cubed sine x dx. Now you need to integrate both sides. You integrate this, you also integrate this. And you know, integral and derivative are inverses of each other. So what we have on the left-hand side is simply y over x squared. Y over x squared is equals to, how do you integrate the right-hand side? This is a product of two functions of x. X cubed is algebraic. Sine of x is trigonometric. We are going to use integration by parts. Look at the rule. It's called LIATEC. So whichever comes first, that will be your u. Algebraic comes before trigonometric. So we are going to say let u be equal to x cubed. And now the remaining will form dv. dv will be equal to sine x dx. Now to make your work easier, use tabular integration because u is a polynomial. Because u is a polynomial, this is polynomial. Every time your u is a polynomial, it is advisable to use tabular integration to save even your time. So tabular integration, that's what we are using. Tabular integration. So I only need to know what is u and the other one I'll have dv over dx. Our u is x cubed, dv over dx, that is sine x. So let's proceed to find the derivatives of the first column until you get to 0, then the integrals of the second column. So let's differentiate x cubed, that is 3x squared. What is the integral of sine x? What did you differentiate to get sine x? It was negative cosine of x. Proceed, derivative of 3x squared, that is 6x. What did you differentiate to get negative cosine of x, that is negative sine x? Proceed, derivative of 6x, that is 6. The integral of negative sine x, what do you differentiate to get negative sine x? That is cosine of x. And finally, differentiate 6, you get 0. Integrate cosine x, that is sine x. So now, once you have that table, you now link these values in the first column and the second column. This is linked to this. Even this is linked to the other one in that manner. So there are 4 arrows. Here you are going to write positive, negative, positive, there's a plus, and finally negative. They must alternate from positive, negative, in that order. So now let's go back to our integral. Those arrows mean multiplication. Multiplication. In fact, this I can draw this here so that I can have enough space to write. Let's be here. So this one, look at the first arrow. It means I'll have x cubed times negative cosine x, then the sign is positive. Positive x cubed times negative cos x. That will be negative because a positive times a negative is negative. So here I expect to have negative x cubed cos x. We are through with the first arrow. Second arrow is negative of 3x squared times negative sine x. Remember, negative times a negative is positive. I expect here to have 3x squared sine x. The other one, sorry, positive 6x times cos x. So I'll write here positive 6x times cosine of x. And lastly, negative 6 times sine x, that is negative 6 sine x. And remember to write the constant c of integration. Now, that is our general solution, where c is an arbitrary constant. You could make y the subject if need be, or you could just leave your solution as the one that we have found there, but it is always advisable that you simplify your solution. So you can say, or y over x squared is equals to, you see, I want to combine the cosine, this and this one. So that will be 6x minus x cubed. 6x minus x cubed. This is times cosine of x. Now also combine the signs. Sine x, I can see there's plus 3x squared minus 6 sine x. Then there's a constant c of integration, or an arbitrary constant. So that is our general solution in part B. Let's work out part C. we see what we're going to get. So finally, in part C, we have x plus 2y cubed, x plus 2y cubed dy is equals to y dx. Now, if you look at the variables here are x and y. Look at the powers. You realize that I can see y cubed. So y cubed here means that this equation cannot be linear in y because of the y cubed. I told you for it to be linear, that variable must be raised to power 1 only, not any other power. So it means we only remain with x because in x, I can only see x raised to 1. There's no any other x raised to any other power. So this equation is linear in x. So it means x will be the dependent variable, not y. So what I need to do is to write this equation in terms of, in the form, dx over dy plus p of y times x is equals to q of y. So I need dx over dy. So what will we do? We divide both sides by dy, also here by dy. So you see dy and dy will cancel. So therefore, we have x plus 2y cubed is equals to y dx over dy. I must make sure that the coefficient of the derivative is 1. So get rid of this y. So again, you divide both sides by y. Also here by y. So that what do we get? Remember, this y will now cancel with this. So we now remain with dx over dy is equals to x over y plus 2y squared. I have divided this one. Now we need to rearrange it. All the functions of x should be on the left-hand side. Anything that depends on x, those terms containing x, must be on the left-hand side. So write or dx over dy minus 1 over y times x is equals to 2y squared. That's what we have. And so this linear ODE in the dependent variable x. So let's comment on this one. You write this is linear ODE in the dependent variable x. So look at the coefficient of x here. That's negative 1 over y. This is a function. This is p, a function of y. So we need to integrate it. The integral of p of y dy is the same as the integral of negative 1 over y dy. And that should give us negative natural log of y, which if you apply the laws of logarithms, this can as well be written as, this you can also write as natural log of y raised to negative 1. So therefore, our integrating factor is equals to exponential the integral of p of y dy. And so this is the same as exponential. What was that integral? It was ln of y raised to negative 1 And since I told you that exponential function and logarithmic functions, or the natural logarithmic functions, those are inverse functions of each other. So our integrating factor will now be equal to negative, no, not negative, but y raised to negative 1, which you can as well write as 1 over y. So once you've found the integrating factor, the next thing is to multiply the ODE. The one we are calling equation star is this one here. Multiply that equation by the integrating factor. So you can write multiply equation star by the integrating factor. So when you multiply, what do we get? It will be this 1 over y times dx over dy minus 1 over y squared times x is equals to 2y squared times 1 over y. That will be 2y. Then take note how the left-hand side can be rewritten. So this left-hand side is the same as derivative with respect to the independent variable. And in this case, our independent variable is y. So it is d dy of the product of dependent variable is x. The integrating factor is 1 over y. It must be product of dependent variable and the integrating factor. On the right hand side, we have 2y. So if I cross multiply by dy, we'll now have derivative of x over y is equals to 2y dy. And now you can integrate both sides, integrate this and also this. So this integral, this derivative, they'll cancel out because they're inverses of each other. So that what we have on the left is x over y is equals to, what is the integral of 2y with respect to y? That will give you y squared. And now don't forget to write the constant c of integration. Remember, the constant c of integration is only written in the final solution. Don't write c when you're finding the integrating factor. So what you have found here is our general solution. Of course, we cannot find the particular solution because we are not given the conditions to apply. So this is general solution. So that's how to solve linear ODEs of the first order and of first degree. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems in ODEs of the first order and first degree. Bye-bye.